So, welcome all. As we were discussing something about internet protocols. So, till now we have seen that internet protocol is a protocol in network layer, which is being used in transmission from one node to another. Right now, we have seen that it was best effort delivery where it was unreliable and connectionless protocol, and we were going through the different fields in its packet format. So in its packet, we have seen that there will be a 20 to 60 byte header, and other part will be data. In header, we were going through that there will be a version, header length, service type, total length, identification flags, and fragmentation. These three fields we left to see today, where which is related to fragmentation, right? Next is time to live and protocol we have seen, and then header checksum. We will try to see this today. Then source IP address and destination IP address, and then options. So we have seen other fields. Let us go through the fragmentation today, where we should understand that the datagram which starts from the source towards the destination, what happens in the IP address, sorry, in network layer, it processes it, right, and determines what to do with this data. When it started from the source, it was known uh, till the next hop. So what was known? I mean, the capacity of the network, the physical layer network, and accordingly the frame was built, right, in the returning layer. However, now what happened when it reached to the next hop, next router, then this router decapsulates it and processes it, and then tries to understand what are the network layer, sorry, this physical network capacity, right? So again, it encapsulates in a new frame according to the um, network, according to the physical capacity. So the capacity of the next network will definitely affect the data size. So if we have received a larger data size, and on the network on which we are going to send, it is of a different kind, and where data size should be small, in that case we will have to fragment our data. We will have to divide our data into multiple chunks. That is fragmentation, right? So basically it will work on our IP datagram. Only this datagram, only data in this datagram will be fragmented. The header will not be fragmented, right? So header will always remain there, header will be there in the frame, and the data, which is the data part of the datagram in IP, it will be fragmented, right? So fragmented according to the capacity of the network. We are calling it MTU, maximum transmission unit, right? So it will be dependent on the data link capacity. So we will fragment our data part of the IP datagram into multiple chunks, each chunk of the capacity according to the physical network, right? So we are calling it MTU, maximum transmission unit. Now, other thing was the 2-bit, sorry, 3-bit flag. Uh, one bit is not used. Another bit was D and M. D is for do not fragment, which shows that the data, the packet that you have received is not fragmented. And M means more fragments. It means that the data has been fragmented, and you are going to receive more fragments of this identification. Okay, so M is something which bit is set. If the bit is set, it means that more fragments are coming, right? D means data has not been fragmented, or it also means that it is the last fragment. No more fragments are going to come, right? So it will be distinguished with the identification number. Okay. So what happens in offset? It is a 13-bit field. What happens in this 13-bit field? It will tell you which chunk, which fragment it is, right? Fragment offset will be 0 if data is not has been fragmented, right? However, if it has been fragmented, then in that case the data is in multiple fragments, multiple chunks, right? So maybe if your data has started from 0 to something 39999, right? So you are dividing it into 8 bytes each or something. In that case, you will have your particular offset. Offset will tell you the starting address of the particular fragment, right? So it is unit of 8 means we are dividing it to 8 bytes, but the chunk will be multiples of 8 bytes. That is what you have to understand. Okay. So 0002 something, maybe whatever 1000, right? And then let me tell you 002 say 1400 you wanted, so 1399, right? And then the next chunk will be the starting address will be this thing 1400, है So now what happens, this 1400 is divided by 8. Each unit is of 8 bytes, so the starting address of the first fragment was 0. So 0 divided by 8 we will get 0 only, so this offset was 0. However, in the second case, your starting address was 1400, it will be divided by 8 since our unit is 8 bytes, so you got the address 175. Similarly, if you have this thing 2800, you get the 355, right? So it may happen that the first fragment was transferred on a particular um, path and other fragment on a different path. This is possible. So a chunk which has been transmitted on a different path, later on, if needed, this fragment can be fragmented again. Okay. However, we will remember this fragmentation kind in our setup, right? So let us assume what happened. This was our data. The identification, you can see identification was 145567, right? So now what happened? This is the total size 4020, right? 20 means 20 bytes of header and 4000 bytes of data, right? This was the total size, na? So total size is 4020 bytes. So what happens here, you are sending something 4000 byte data. You divide it into 3 fragments, 1420, 1420 and 1220 bytes. 20 is actually the header and 1400, 1400 and 1200. Now later on you transmitted these 3 fragments on 3 different paths, and on this path you again realize that the capacity is low, so we will have to fragment it again. Now one thing that you have to understand here is it has already been fragmented, in that case the fragment address, sorry, the offset was set, है 1 means, here see, it was 1 means more fragments are coming, 1 means more fragments are coming, it was 0 means it is the last fragment. Okay, now it was 1. Now what happened, we saw the this offset, it was 175. So while dividing, what we did, we started with 175. This we divided into, we wanted 800 bytes here, so 175 divided by so this 800 divided by 8, we got 100, right? So after 100, it was 175. The next address of here will be from 275, है so that is how we divided this 1400 into 800 and 600. So in this way fragments can be made up. So this was the whole process of fragmentation. So basically 3 fields that you have to understand here was this identification. This will be 16-bit identification number. Other 3 fields, this is always blank or something, we will leave it, and this will be D and M, right? So now we are going for option field. We understand that there is maximum size 60 byte and minimum 20 byte for the IP header. So IP header is of 20 bytes and rest is option field, 40 bytes, 0 to 45. So option field is optional, we understand. So what actually we keep in this optional field, you know? We will have to understand that in this optional field we will try to keep optional things if at all required. Say here in the first 8 bytes we are trying to store some information. 1 bit, 2 bit, sorry, first 8 bits, 1 bit, the next 2 bits and next 5 bits. So in the first bit we are storing something information of copy. This 1 bit actually controls the presence of the option in fragment. When its value is 0, it means that the option must be copied only to the first fragment. If at all the value is 1, it means option must be copied to all fragments. Okay, the next 2 fields, next 2 bits define the general purpose of the option. When its value is 0 0, you see it means it is datagram control. Now when its value is 0, it means that the option is used for debugging and management. The other 2 possible values, 0 1 and 1 0 1 1, it is reserved, not used. Right. The next 5 bits, actually they define the type of option. So only these 6 types are in use, although with 5 bits different kind of 32 options are can be used. However, for now we have only these 6 types. So what happens in these 6 types? Actually there can be no operation, end of option, record root, a strict source root, loose source root, timestamp, where we define some options like no operation is to be performed, or we define some bits to so that it is end of option, or end of option or padding kind of things can be done. This is a record root, means initially these fields will be empty, and as it will go through the routers, it will keep on storing the address. A strict root means you will define the particular root of the packet. We will define the next router, and for means all the hops, whatever uh, hops are possible. Actually, 9 hops, 9 fields, 9 IP addresses can be defined here. That is the possibility. Loose source root means you will fill the source root, sorry, the root. However, in between it can change also. Timestamp is where we will provide the root. This is the root. However, some information like timestamp, at this particular timestamp it reaches to this particular node, that there will be a field and it can be stored. These are the things for which it is used. Now the next thing is checksum. So basically it is used for error detection. Hmm. So what happens actually, while transmission of your packet, some bits may get corrupted, or means some extra bits can be included, or some bits can uh, multi multiply itself. These kind of things may happen. So some redundant information. Okay. Now what happens? Basically, you send some information of the header, IP header, along with the IP header. Okay. So in checksum, what you do on the sender side, you calculate some value for the IP header and send it along with the packet. On the receiver side, we repeat some kind of calculation, and there we get some value, and if the value, the result is satisfactory, we accept the packet, or we reject the packet. So what actually happens at the center side, in the header we have different fields, right? So we divide into n bit fields. Actually our checksum is of 16 bits, so we divide the packet into 16 bits. So first 16 bit, next 16 bit, and so on, all the 16 bits, we keep the checksum at 0 and add all these values, and then we get some n bit value, right? And after that, this n bit, we complement it. And we get this n bit value. We call it checksum. So basically, we get the sum of these values and we complemented it. Now we send this n bit checksum with the packet to the receiver, and this receiver, what it does, it performs the sum of all the all the 16-bit values, right? N bits means 16 bits, 16 bits, all the 16 bits, and the checksum, the same checksum what receiver has received, right? And you can understand that this was the sum of all of these things, all of the other 16 bits, and checksum is its complement. So when we will when we will add all these fields along with the complement, we must get 0. So that is the concept. So here we add all these values, and here we get the n bit value. Yeah. Then we complement and we get get the n bits. Now if this result is 0, we accept the packet or we discard the packet, right? So some of these values were, if it already was t, the checksum is minus t. So t and minus t sent you, right? T and minus t will give you these n bits, which is minus 0. Okay, you will perform the complement, then you will get 0. Okay. Then the next thing that you are going to do, see, in the checksum, actually only the IP header is covered. only the IP header is covered, huh? Not the data part. So IP header part for the fields, the 16-bit divided fields in the IP header, it will be uh, considered for finding checksum, not the whole data. Now let us see how the checksum is being calculated. As I told, the 16 bits will be considered. So this 16 bit, 8 bit, 8 bit, and this 16 bit, right? 8 bit, 8 bit, and this 16 bit, next 16 bit, next 16 bit, है in this way all the 16 bit. Here is the part of this thing, 0, right? This 0, say 4 and 17, है this was the value of this field. This yellow part is all 0 here. The sum is something, and then we complemented it and we got it, the checksum. We kept this checksum again in this uh, place and sent this packet to the receiver. What happened to the receiver side? It received something. It then after that it performs the addition of all these things. It got something and it complemented it and got minus 1, minus 0 actually, and then it complemented and got the 0. Then it confirmed that yes, I have received the correct packet. So actually in the last, what we are going to see is all the components in the IP module, the software that you will build. In IP, actually what happens, you will start with this header adding module. You will get the data from the above layer, and then you will add the header. So you will have a module for adding the header part. All these fields accordingly, the bits related to the field will be set, and it will be uh, added with the data. You will get the IP packet. Then you will have a processing module where you will decide the packet is coming from the upper layer or from the lower layer. So accordingly you will forward to the forwarding module or a reassembly module. If at all it is coming from a lower layer, data link layer, you will forward to reassembly layer, where it will be the IP packets will come, IP header will be removed, and data will be given to the upper layer. If at all it is coming from the AO layers, the IP packet will be forwarded to forwarding module, which will forward to the next layer. So what will happen in this forwarding module will add its if at all it needs to fragment it, then it will add the fragmentation details, fragment the packet. If at all not to be fragmented, and whatever needed it does, and uh, forwards it to the data link layer. So in this way, if you are going to design this IP module, you will have to keep these things in mind. That is only for IP. Next we will see some other protocol in the next video. Thank you.